So today our goal is going to be to compute multiplicative inverses modulo n. This is a surprisingly tricky problem, which is actually going to lead us into some basic number theory. It's very cute. We're going to have to understand a bit more about the notion of the greatest common divisor between two integers. It's neat stuff, and it's going to require a few tricks that are a little bit surprising. So let's go. Okay, so let's just remember what is the greatest common divisor of two positive integers. We say that if you're given x and y, which are positive integers, then the GCD of x and y is the largest positive integer that divides both x and y. So it's the largest number that goes into x and also goes into y. Okay, so let's just consider an example here. What's the GCD of, I don't know, let's say 42 and 78? Okay, what's the GCD of these numbers? Well, kind of the easiest way to do this in your head, if you're good at factoring, is basically to write these numbers in their prime factorization. 42 equals 2 times 3 times 7. And by the way, I don't recommend this computationally, doing it this way. We're going to learn soon that factoring numbers is not generally easy for large numbers, but for a small number like this, it's not too bad. 78 equals, well, divided by 2 is 39. So that equals 2 times 3 times 13, right? So you can see that 2 and 3 here both divide 42 and 78. So 6 is going to be the greatest common divisor of 42 and 78, right? It's the largest integer that divides both of these numbers. Now I'm going to give you a lemma that actually is surprisingly useful to reason about the greatest common divisor in multiplicative inverses. So let's say you have x and y are two positive integers. Assume you have some integer d that has the following two properties. D divides both x and y. And also you can write d is a integer combination of x and y, meaning you can write d is equal to ax plus by for some integers a and b. It turns out that you can then be sure that d is the greatest common divisor of x and y. We can actually prove that. The proof of this lemma is really beautifully simple. It requires making two observations. First, let's let k equal to the greatest common divisor of x and y. Notice that d is a common divisor of x and y by assumption. It divides both x and y. Therefore, d has to be less than or equal to k, because k is the largest common divisor of x and y. So we have the inequality d is less than or equal to k. On the other hand, since k divides both x and y, it's a common divisor of x and y. In fact, it's the greatest common divisor of x and y. Then k also has to divide any integer combination of x and y, right? If you take any integer combination ax plus by, then k has to divide that number as well. But that's d. If k divides d, then k has to be less than or equal to d, right? So we have to conclude here that k is both bigger than or equal to d and less than or equal to d, and therefore we can conclude that k must be equal to d. Okay, important question. Why am I so interested in computing the GCD of x and y? Right? Why is that important for getting multiplicative inverses mod n? That's a good question. If we can compute GCD of, let's say, x and n, right? Here I'm looking to get the x inverse mod n, the multiplicative inverse of x mod n. Let's say I can compute GCD of x and n. You may remember that I stated that if that equals 1, that holds if and only if x has an inverse mod n, right? I told you that in a previous lecture. So let's say that that's true. Let's just believe that fact for now. If GCD of x and n is 1, remember from that previous lemma that we just showed you, we can then write that ax plus bn equals 1, right? We can write it as a linear. We can write 1 as a linear or the integer combination of x and n, and let's just say that the multiples are a and b, right? The integer multiples are a and b. If that's the case, then what can we conclude, right? If we can write the greatest common divisor, which is 1, of x and n, as ax plus bn, then you'll notice that, therefore, AX is congruent to 1 mod n. Why is that true? Why is that true? Well, it's true because you'll notice that I've written AX as being equal to a multiple of n, an integer multiple of n, plus 1. So clearly the remainder upon division by n, if I were to divide x by n, the remainder would be 1, just looking at this expression right here, right? But if AX is congruent to 1 mod n, I just found my multiplicative inverse mod n. What is it? It's A. A is my multiplicative inverse mod n of x, right? So this implies that A equals x inverse mod n. Or at least I should say A is congruent to x inverse mod n. Okay, so now we're interested in actually getting an algorithm that's efficient for computing the greatest common divisor of two integers x and y. For now, assume that the first input is always bigger than or equal to the second input, so x is always bigger than or equal to y, and they're both bigger than 0. How are we going to get GCD of x and y? We're going to need this little simple observation of Euclid, we'll call it Euclid's rule. So what Euclid observed is that the GCD of x and y is also the GCD of x minus y, comma y. So why is that? So I won't do necessarily a formal proof here, but if you just think about it, any divisor of x and y also has to be a divisor of x minus y as well. So a divisor of x and y, and particularly the greatest common divisor, would also be a divisor of x minus y and y. Similarly, if you're a divisor of x minus y and y, then you also have to divide x and y. So you'll notice that all of the divisors of x and y are the same as all of the divisors of x minus y and y, and therefore they have to have the same greatest common divisor. Okay, there's also a more advanced version of the Euclid's rule. We'll call it Euclid's rule 2.0. If you look at the greatest common divisor of x and y, that actually is also the same as the greatest common divisor of x mod y and y. Why is that? Okay, this is true simply because x mod y is simply the remainder upon division by y, right? The remainder of if you divide x by y, which just means that you're taking x and you're subtracting off as many copies of y as you need to until you have a remainder which is less than y. So to get this statement that the GCD of x and y is the same as the GCD of x mod y, comma y, I get this statement by simply applying Euclid's rule 1.0 q many times, right? I keep subtracting y off of the first argument of the GCD until I get down to this remainder. And that's how I get Euclid's rule 2.0. Okay, so Euclid's rule 2.0 actually suggests an almost trivial algorithm for computing the greatest common divisor. You'll notice that by simply reducing the computation of the greatest common divisor of x and y to the greatest common divisor of y and x mod y, you can simply use that to get a recursive algorithm. X mod y is certainly going to be smaller than x, so you're reducing the size of these two integers and shrinking them, and eventually that has to bottom out, so you can be sure that this recursive strategy will eventually finish. What this algorithm doesn't tell you, obviously, is what the running time is and how quickly you actually get to a base case, and that is something we need to think about a little bit. So what we need to establish the running time of this Euclid algorithm is just one little observation. I won't prove it precisely, but I suggest you try this at home to think about why this is true. If x is larger than y, or at least as big as y, then it's certainly the case that x mod y is less than or equal to x over 2. Just think about that for a little bit. There's sort of two cases you have to worry about, whether y is between 0 to x over 2 or whether y is between x over 2 and x. But in either case, you can be sure that x mod y is going to be no more than x over 2. Now, why is that useful? Let's see why that's useful. Let's just think about what happens to the inputs to the Euclid's algorithm after two steps of this recursion. First, you got inputs x and y, where x is bigger than y. You then converted that into inputs y and x mod y. And then after a second iteration, the first input was going to be x mod y, and then something else. I don't care about that second term. But you'll notice that the first term, which was x, right, which is the larger term, so it's the larger of the two inputs, went to y. Oh, went to y, and then went to x mod y. After 2 steps of the algorithm, the first input to GCD, to this Euclid algorithm, went from x to x mod y. So it reduced by a factor of 2. So you'll notice that after not 1 step necessarily, but after 2 steps, I was able to reduce the first input, which is the larger input, by a factor of 2. That's important for thinking about the running time. So before each recursive step of this algorithm, you'll notice that we have to compute x mod y. Well, that requires dividing x by y and finding the remainder. That's an O of n squared algorithm. We'll need an O of n squared algorithm for that. We might be able to improve upon that, but roughly speaking, an O of n squared algorithm as a decent upper bound. And then, to ensure that we reach a base case, we'll need to perform on the order of n recursive calls. That's because every time we do 2 iterations of this recursion, we have the size of the first input. And eventually we'll have to have it about n times before we get down to a base case. So in total, this algorithm requires on the order of n cubed to compute the GCD of x and y. So in order to actually compute the thing we want, which is multiplicative inverses of integers x mod n, right? We want to get x inverse mod n. We need more than just to compute the GCD of x and n. Of course, we know, if you recall from earlier in the lecture, the inverse of x mod n only exists if the GCD of x and n equals 1. This must be 1 for the inverse to exist. But the question is, how do we actually compute this inverse, right? That's the interesting part. Let's recall something that we mentioned earlier in this lecture. The GCD of x and n actually can be written as a integer combination of the integers x and n, right? You can write it as ax plus bn. And so, of course, if this equals 1, right? If that GCD is 1, that means we can compute an inverse. And in fact, if we had those integers a and b, we would know that this integer a is the multiplicative inverse of x, right? Mod n. And the reason for that is that, as you'll notice, I'm writing ax as a integer multiple of n plus 1, which means that if you try to divide x by n, you would get a remainder of 1. But that's what it means to be the multiplicative inverse of x. You just take ax and have that be a number which is an integer multiple of n plus 1, right? So the thing that I actually want to compute here are these numbers a and b. How do I get a and b along the way? I computed the GCD in the previous slide, but I didn't compute these integer multiples a and b that would allow me to write the GCD in this form. So how can I do that? It turns out it's actually not that hard. It requires a simple extension of the previous Euclid algorithm. The main trick you need is just to extend this Euclid algorithm a little bit. I won't go through all the details of why this works, but essentially what you have to do is maintain these, not just this estimate of d of the GCD of x and y, but also numbers a and b. You make recursive calls to Euclid ext on y, x mod y, as you did before, but the output of that gives you numbers a prime and b prime. You have to manipulate those appropriately and output modified versions of those to get the correct a and b, the integer multiples of x and y that give you the GCD. So you have to use an inductive proof to show that this works. I'll let you guys do that on your own time, but it's a worthwhile induction to try, and it's not that tricky. Let's just finish up with Euclid ext by noting that the running time is O of n cubed. The time complexity of this is no different than the time complexity of the original Euclid algorithm. Let's just finish up by noting that we have almost all the tools we need to be able to construct the RSA cryptosystem and understand why it works. We'll get to that for the next lecture.